Alright, let's look at the Jacobians. Alright, let's say you have a conversion equation. X is written in terms of st and u, and y is written in terms of st and u, and z is the same way, written in terms of st, u. Right, Jacobian, the notation is j is equal to, this is using a partial derivative notation, partial x comma y comma z with respect to st and u. Right, this is just going to be the determinant of this kind of a strange matrix. So we take the partial derivative of x with respect to s, and partial derivative of x with respect to t, partial derivative of x with respect to u. So we take the partial derivative with respect to all three variables. And next one is partial derivative of y with respect to s, partial derivative of y with respect to t, partial derivative of y with respect to u. Right? Of course, last row would be partial derivative of z with respect to s, partial derivative of z with respect to t, partial derivative of z with respect to u. Right? And then we take the determinant of this resulting matrix. This is called the Jacobians. Right? And what we can use for this Jacobian is that the Jacobian kind of tells you the kind of a expansion rate when you do this conversion. So if you are, for example, looking for volume element of in terms of the new new variables st and u, what we can do is this is going to be equal to, right? So originally it's dx dy times dz, but the dv is going to be in terms of st and u would be absolute value of Jacobian, because Jacobian turned out to be negative, so we make sure that it's going to be positive, then times the new variable, so ds dt du. This will give us the new volume element. Right? So let's use this to Jacobian to understand this actually works for area element too, for polar coordinates. Right? We know that the area element for polar coordinates is r dr d theta. Right? Can we get that? Right? So let's find the Jacobian first for this guy. So Jacobian j is going to be, right, so partial of x with respect to, because this is going to be r and theta, so I'm going to do r, partial of x with respect to theta, and actually, sorry, maybe I should do this, or I should use this notation first. Right, here are the old variables with respect to new variable, in this case r and theta. Right, so we take the determinant of partial of x with respect to r, partial of x with respect to theta, partial of y with respect to r, partial of y with respect to theta. Right? Right, let's compute that. So let's find the partial of x with respect to r. So that will be pretty simple. Right, this is going to be, x with respect to r would be just cosine of theta. So we get the cosine of theta there. Partial of x with respect to theta would be negative r sine of theta. Right, partial of y with respect to r would be just sine of theta. And then partial of y with respect to theta would be r cosine of theta. Right? Then you can see that if you take the determinant, I'm going to go down here, so cosine times r cosine theta. So we have r cosine squared of theta minus negative, so it's going to be plus r sine squared of theta. Right? If you pull out r, then you have cosine squared of theta plus sine squared of theta. So since cosine squared plus sine squared is equal to 1, according to the trig identity, you're going to get r. R is a positive value, so we don't have to worry about taking the absolute value. All right, so therefore, area element is going to be absolute value of Jacobian times dr d theta, but the Jacobian came out to be just r, and dr d theta, right? So you can see that this is a familiar area element for polar coordinates, and we can kind of get that using Jacobians. And this can be done for cylindrical coordinates and also spherical coordinates as well. All right, that's it. I hope that this was clear.